Learning generalizable physical dynamics of 3D rigid objects. We investigate the problem of predicting the dynamics of a 3D rigid object that is initially stationary on a plane. The object is subjected to an impulse which leads to an instantaneous change in the velocity. The object moves as a result of the impulse until friction brings it to rest. Our goal is to estimate the resting position of the object's center of mass and the total rotation that the object undergoes. We first show some results of our method that predicts the position and total rotation of the object. Our method can generalize to shapes and impulses that have not been observed before. Our method is trained on different object shapes. It can make accurate and generalizable predictions even for previously unseen shapes, such as the ones shown. We use the 3D shape of the object represented as a point cloud as input to our method. We assume that the object moves along a plane under standard gravity, the applied impulse is parallel to the plane at the same height as the center of mass, and the friction coefficient between the plane and the object is constant. Since motion is most prominent along the direction of force, we use special coordinates that are aligned with the impulse. Our problem formulation is challenging because objects could exhibit complex motions like wobbling, which causes the contact surface area to vary, resulting in complex trajectories. We present a neural network to learn generalizable dynamics for 3D rigid objects. Assuming constant friction, the final rest state of an object depends on its velocity v and angular velocity omega. In turn, these are dependent on the applied impulse, mass, and moment of inertia of the object. We use these observations to design our network architecture, which has 3 branches. The impulse processing branch aims to learn the effect of the applied impulse and angular impulse on the final resting object state. The shape processing branch is responsible for learning notions of volume, mass, and moment of inertia from a point cloud representation. The prediction branch learns to make final predictions using the features extracted from the 2 previous branches. We use 3D simulation data to train our network on thousands of simulations of different object shapes using a physics engine. Please see the paper for more details. We also use hundreds of objects from ShapeNet, a large shape repository, to make our network generalize to previously unseen shapes. Here we show more results. In a few cases, our method produces large errors, which we show here. Here we show qualitative comparison against several baselines. Please see the paper for more details. Here we show more results. Thank you for watching.